So previously, we started this process of use case realizations when we talked about design, which we looked at in the previous unit, really the previous lecture for this unit. So we're going to continue with that. So previously, we introduced the software design concepts for OO. We talked about multi-layer design. We talked about use case realization using the CRC Cards technique and some fundamental design principles. We're going to expand on that a little bit. We're going to talk about patterns for or design patterns in object-oriented software design. So we're going to look at this at a little bit more of an advanced level, but based off of what we've learned so far. We're also going to introduce using sequence diagrams and communication diagrams as well as package diagrams in your design. And again, a lot of this is based off of the standard design patterns, which we'll talk about. So the design is in this unit, we look at doing a design use case by use case, and within each use case, layer by layer, based on the RMO case study that our textbook talks about and that we've been talking about throughout the course. So detailed design of multi-layer systems, CRC cards, which we talked about before, was focused on the business logic. In other words, the problem domain. So we've been talking about the problem domain a lot. What is the problem domain? That's what we're actually designing the system for, is the problem domain. And then around the problem domain, a lot of times we have a structure to support that problem, all the classes and everything for the problem domain. So for example, almost every system has a database, has login, has authentication, has some kind of user interface. All that stuff is the minutia of most systems, all that standard infrastructure that we have to have. So in this unit, we not only talk about, we already, in the previous lecture, we talked about how we use those CRC cards to focus on the business logic, and now we have a basic design based around that business logic, but now we have to do all that infrastructure around that, which is where we start bringing in these design patterns. And the most prolific design pattern, I think, in object-oriented programming is probably the 3-layer or the MVC model. You'll hear it in other textbooks called the MVC model. I've actually seen that more, I think, than the 3-layer design pattern, but it's a view model, a view layer, a business or logic or problem domain layer, and a data access layer, or in the MVC model, what they call the model, view, controller. Model being the database, view being the user interface, and then the controller, more or less the business logic layer. So some questions that come up could include, how do the objects get created in memory? How does the user interface interact with other objects? How are objects handled by the database? Will other objects be necessary? What is the lifespan of each object? So all of those questions, our business or our problem or our domain layer doesn't really handle these questions. So this is what we need these design patterns to help us tackle. And also, we have to expand our design to encompass all of the infrastructure, as I've been saying, that supports that core system and that core functionality. So some design patterns. A design pattern is a standard design technique and templates that are widely recognized as good practice. For common design coding problems, the design pattern suggests the best way to handle the problem. They are written in design pattern catalogs and references, and they include the pattern name, a problem that requires the solution, and the pattern that solves the problem, an example of the pattern. So we're going to take a look at a couple of these, benefits and consequences of the pattern. So we're going to take a look at a few of these design patterns. So design patterns became widely accepted after the publication of Elements of Reusable Object-Oriented Software by Gomma et al., the Gang of Four. And these are the guys also that sort of came up with this whole UML thing that we talk about in this course in object-oriented systems design. So design patterns, when you think about it, a lot of the things that our systems do are reused through many systems. I've already given you some examples of that. For example, I talked about accessing and using a database, user authentication, the front end or the view layer. All that stuff is reused on most systems. You use it over and over again. So those are patterns. What changes is what's in the core of the system, that business or that problem domain, the business logic is what changes. So we can surround that with some standard components, and we can use these patterns to follow that same template. So there are architectural design patterns, which we talked about already. That would be things like the 3-layer or model view controller architecture. The first example of a programming design pattern shown is the controller pattern. The problem is deciding how to handle all these messages from the view layer to classes and the problem domain layer to reduce coupling. So the solution is to assign one class between the view layer and the problem domain layer that receives all messages and acts as a switchboard, directing messages to the problem domain. So we already talked about coupling and cohesion, and how these, how we want to use those. We want to use those concepts in our, or those are good things to have, high cohesiveness and low coupling. So if we don't want to have different components very tightly integrated and have them more loosely coupled, one way to do that is this controller pattern, which we talk about. So we're going to look at an example of the controller pattern. So that's the first one that we talk about in this unit. And in your textbook, if you look at, they have an example of the controller pattern. So it describes the problem, describes the solution, and there in the middle you see a nice example of it. So there's our customer form, which is on the user interface side. And then we have a handler, which handles the customer form and creates that customer object or uses that customer object. So that customer handler is a controller class. So that handles the customer, all the communication between the user interface and the class that represents the problem domain. So some more design patterns. We have an adapter pattern. So just like an adapter, think about VGA to HDMI as an adapter. It adapts from one technology to another. We do something similar in object-oriented programming and object-oriented design. So to give you an example, let's say you have a class that does something. Maybe it talks to a database. Maybe it inserts records into a database somewhere, or it represents that data structure. And let's say you need to change to a different database engine. So you've got a couple different options there. One option is, or you want to be able to support multiple database engines. One option is you could rewrite that class for each database engine, right? So you can have a different class that works for each different database engine, and depending on which one you're using, it would instantiate that particular class. But then you have to rewrite that code for each different database engine. So instead, you could write an adapter class. In essence, you write a class that knows how to handle each of the different databases, and then the class that passes information to it does so in a standard or a structured way that you don't have to write different classes to pass that information back and forth. So that's an example of an adapter class. Another example is a factory class. So you use a factory class when the creation logic is complex for a set of classes. In other words, maybe creating a customer object is very complex. There's a lot of stuff that has to happen. It's a very complex class. So creating an object from that might be difficult. So you can have a factory class that does that for you. So you can write factory classes that can go out and create these objects. So you just instantiate a method in the factory class and tell it, go create me a customer, and it does all the things that it needs to do to create that customer. We do this in my industry, where I work. I probably mentioned before, I work in medical imaging, and there are some very complex standards in medical imaging to manage how images are formatted and the metadata and all that stuff. So we could use a factory class to create one of those image objects. And it has all the stuff that it needs to comply with the standard, and it sort of gives us a whole object that it's ready for us to go and do stuff with it. Whether it's manipulating an image or adding new images to the object or what have you. So that's an example of using a factory class. Another example they talk about in your textbook is the singleton design pattern. You use this when only one instance should exist at a time and it's shared. So I'll give you an example. Let's say you've got a system that uses a database and you only want one connection to that database. So you could have a singleton design pattern that says I can only create one instance of that database connection object, and everything that uses the database uses that one object. Now, I think, if you read about the singleton pattern, sometimes it's overused a little bit, and some developers tend to rely on that singleton pattern, I think, and designers, analysts that are doing what we're talking about doing, might use that singleton pattern and kind of turn a program back into being procedural, because, this whole object-oriented thing can be a little bit complex if you're not used to it. And if you're used to the procedural world, I think some people get kind of back in the habit of doing things procedurally, and they might use a singleton pattern to do that. So something certainly to watch out for. All right, so this is from your textbook. When you look in the textbook, you'll see a write-up for each one of these design patterns we talked about. So here was the adapter design pattern, and you can see here we've got our system, We've got the tax calculator, and then a tax calculator adapter, and ABC tax calculator. So in this case, there might be a tax calculator class that we have in our system and maybe some third-party tax calculator, and we have an adapter between the two, maybe for different countries or something like that. A factory design pattern. So if you recall, the factory can create an object from, you basically tell the object create, or tell the factory to create an object. That's kind of what's happening here. So we have our factory on the bottom right-hand side. We've got our system, and our system uses the order DA. But to create an order DA, we can use the factory to create that object. So just a very simple example. And you can take a look at this in your book. There's a nice little write-up about this and how it works. So here's a singleton design pattern. Here they just have some code. You might see this code on the test, so take a look at that. But basically, again, a singleton pattern is where only one instance of that object can exist, and everything uses that one object, just as a simple example. So again, this is in the textbook, and you can take a look at that in the book. All right, so now we've got these design patterns figured out. Let's take a look at doing some modeling techniques that are a little bit beyond what we've done so far with the class diagram. So we talked about design class diagrams in the previous presentation. Now we're going to talk about sequence diagrams, which of course goes hand in hand with all the other models that we've talked about. So use case realization is the process of elaborating the detailed design of a use case with interaction diagrams. Two types of interaction diagrams. We have sequence diagrams, which is emphasized in your textbook, and we also have communication diagrams, which are kind of introduced in your textbook but not elaborated on into any detail. We're going to take a look at both of these. So a sequence diagram, aka use case realization sequence diagram, extends the system sequence diagram. So earlier we talked about the system sequence diagram, where we showed the actor and the system and how the actor interfaces or interacts with the system, right? So it's an interaction diagram, and it shows you that over time. Now we talk about the sequence diagram showing all of these different classes or objects, specific instances of objects in our system and how they interact. So it's a lot more granular than in our system sequence diagram. Our system sequence diagram was pretty simple. It was the actor and the system. But now we're going to expand on that and create a much more detailed sequence diagram, and that's our design sequence diagram or our use case realization sequence diagram. So you'll have all the different objects that we have to deal with, such as the view layer objects, domain layer objects. So the view layer is what interfaces with our actors or with our our interfaces. And again, that could be both other systems and our people that are using the system. The domain layer objects, which we usually do first because it's easier to visualize and understand that. It's sort of the core functionality of the system. Everything we do is to support that domain layer. And again, domain being the problem domain. So the thing that we're actually designing our system, the problem we're actually designing our system to solve. So we'll have in our sequence diagram domain layer objects and data access layer objects. And again, this is all assuming that you're using the 3-layer design pattern, which, as I said, is very common. And most of the systems that you design in the field would probably use this method. So we can start with a system sequence diagram. So here's a system sequence diagram that's from the textbook. You can see we've got the clerk, which is our actor, and it's interacting with the system. So the clerk creates a new customer with a name, a phone, and an email. They get back a customer ID, a name, a phone, and an email. Then they enter an address, and then they enter a credit card info, and so forth and so on. And notice the timeline is time going down. So we can see here that the first thing our clerk does is create a new customer. Then they enter an address, and then they enter the credit card information. So again, we looked at this already. This is actually from one of the previous presentations. We looked at this already. So this is the system sequence diagram. So we can start with this, and we can expand on that. So now we can expand that system. We can decompose the system into additional objects. So we have an instance of the customer form. We have an instance of the customer handler, and we have an instance of the customer object, which is the one on the right-hand side. And you got some labels up here that show us that the customer form is the view layer class, right? So that's the view side of our 3-layer. Now in this diagram, notice there's only 2 layers, right? We've got the view layer and the domain layer class, but there is no data access class. So there's no model in the MVC in the MVC pattern. There's no model layer, so there's no database layer. Also, something else to notice is we talked about stereotypes before, so we can see it in action here. The customer handler has a stereotype of controller because it is the type of class this is a controller class. In a sequence diagram, it's typical to think of each of those class names. Those are instances of a class, or instance objects that are objects are instances of an object within the class. Sorry. So that's an actual customer form. We have a customer handler, and we have an instance of the customer, and we can think of it that way. So create new customer is, again, looking down the left-hand side from the clerk, that's all the stuff we stole from the system sequence diagram. So we have to keep that stuff the same. We can't just create new stuff here. If we find that we have to have additional messages with that customer form from the actor, we would have to go back and add that to our system sequence diagram to make sure we capture that. So, again, we're basing this off of that system sequence diagram, which we did in the analysis phase. So we start with that. We decomposed into a couple different classes. So my clerk is essentially using the customer form object. They create a new customer. Once the customer form handles that request, it's going to call controller, the controller class, the customer handler, I should say controller stereotype. And notice that it's calling create new customer, and it's getting back an object. So there's an object reference there where you see the AC : equal. That is an object that it's getting back. So we should be getting back a customer ID, a name, a phone, and an email, all in that object. And notice as well that when create new customer is called on the customer handler is actually going back and working with the customer object itself. And the customer object is working directly with SQL. So we're missing that other, that data level or that data layer, that database layer. So you can follow the logic here, and you can see the communication and how these different classes or objects within, instances of objects from those classes interact with each other over time, and you're reading straight down to read that over time. So some notes on that diagram. I talked about all of this. So this is a two-layer architecture as the domain class customer knows about the database and executes SQL statements for data access. So when we looked at that before, that customer object was interacting directly with the database, which is not best practice according to our design patterns. So we'll talk about that later. The three-layer design would add a data access class to handle the database, resulting in higher cohesiveness and loose coupling. Why is it higher cohesiveness? Because the customer object right now is both working, both a customer and doing all the things that we have to do. It has all the responsibility of managing a customer object, but it also has to work with the database. So it's really kind of doing two things. So we can get higher cohesiveness by creating another class that works with the database. Then our customer class does not have to do that. We can get looser coupling because if you think about it right now, if there's anything that has to change in the database, maybe the database schema, maybe the way the keys work, or even the database engine itself, we have to actually change that customer class to make those changes. So we have very tight coupling there. But if we add a database class, then we can get more loose coupling. It's a much more loosely coupled interaction, which is a good thing. We talked about how that's better. We always want to go with the option that results in more loose coupling. So I talked about this as well. We talked about the customer form as an object of the customer form class, and customer handler is an object of the customer handler class, playing the role of a controller. And that's why we had a stereotype of controller, which I pointed out. I also pointed out that AC customer was an object of the customer class, known by its reference variable named AC. And you would have seen that in the class diagram. So we looked at the design class diagram in the previous presentation, and we did have that. We had an AC variable name or a AC attribute which referenced the entire customer object. So the data type of that attribute was the entire customer object. Note that the create message to AC customer points to the object symbol to indicate create. All right, so let's take a look. This is the create customer account use case we're talking about here. This is the class diagram. So here you can see all the relationships between these, between all these classes. So we can change this. By the way, this is sort of a database diagram, more or less, but we can change this into our first cut design class diagram for the use case. So here we've got our controller, the customer handler controller class. We have the customer class itself, and then the customer class has an account and an address subclass. So account and address are subclasses or inferior to the customer class, or subordinate to, rather. Pardon me. So create customer account use case. So again, we have create new customer, enter address, enter credit card. There's that controller class. We have the customer address and account. This might be the second version where we expand on that interaction between the controller class, the customer handler, and the customer, and then the customer interacting with address and account classes, those objects for address and account. This is a communication diagram. So the customer object starts by searching for a product, looking at product reviews, and then selects options and quantity. They add it to their cart, and so forth and so on. So we're gonna expand on this a little bit. So here's our customer interacting with the system to fill their shopping cart, as an example. So again, this is from our analysis phase. We would have created this diagram in the analysis phase. We're going to again decompose the system into the components that are required. Now we know from the CRC cards that we talked about, or from our first cut design class diagrams, we know that these are the classes that would be involved in the process. So we would place all those classes on our sequence diagram and explain the interaction or show the interaction over time between all those different classes. So again, we started with I'll take a step back here. We started with our system sequence diagram, which shows the interaction between the actor and the system. Then we take a look at our design class, our class diagram from our analysis phase and from doing the CRC cards. And we know that these are all the classes that are going to have to be involved in this process of filling a shopping cart. So then we take all those classes and we decompose that system timeline into all the different classes that would have to interact with each other to carry out that timeline. So we have our cart handler, our customer, online cart, cart item, promo offering, product item, and inventory item. And if I take a step back real quick, you'll see that all of the classes that we know are involved in the fill shopping cart use case are shown in our system or on our design class sequence diagram. All right, so some assumptions that we make as we've been, so far, some of the assumptions that we've made. Perfect technology assumption. We've talked about this before. We first encountered this for use cases. We don't include messages such as the user having to log on. So we don't have to include things like logging on or messages that say log into database, or connect to database, establish connection, all those things we don't have to put on the diagram. The perfect memory assumption is the assumption where we assume that the necessary objects were in memory and available for the use case. So in the multi-layer design to follow, which we're going to talk about, we do not include the steps necessary to create objects in memory. Of course, this would actually have to happen when you start writing code, but we don't have to put that in our diagrams. We don't have to talk about that stuff. The perfect solution assumption, the first cut sequence diagram assumes no exception conditions. So nothing goes wrong in our first cut sequence diagrams, but we would at some point have to handle exceptions, and we would have to somehow diagram that stuff. Separation of responsibilities, the design principle that recommends segregating classes into separate components based on the primary focus, such as user interface, domain, and data access. So developing a multi-layer design, we talked about the view layer. With users, there is always a view layer. We have to have forms or pages or reports and things like that. We have a data access layer. Data access, which is your persistent classes need some mechanism for storing and retrieving their state from a database. So, something that can talk to the database essentially. Separate layer required when the business logic is complex and there is a need to separate the connection to database and SQL from the domain classes, which is pretty typical. Create customer account use case might not need a separate layer as domain classes can handle data. Fill shopping cart is much more complex and does need it. So we take a look at that. For each domain class, add a data access class to get data and save data about an instance. So there's our example of the fill cart. And you notice here that in the with the fill cart, we now have classes for data access. So we added 3 classes, the promo offering, product item, and inventory. And also cart item, sorry. So notes on data access. Cart handler, find customer account number message to customer class means customer should create a new instance named AC, send the message to customer DA asking for it to read info from the database for a customer with that account number, and then populate the new customer instance with attribute values from the database. So let's rewind real quick. Take a look at the customer handler. Notice the customer handler, the AC customer, sends a message to customer DA. So it sends a message to customer DA, which goes and gets the customer information from the database. So that's what they're talking about there. The other times a domain object is needed, a similar pattern is used, such as when needing information from promo offering, product item, inventory item, and cart item to display in the online cart, promo offering DA, product item DA, and inventory item DA. So all the ones that say DA are data access classes are asked to find the data and populate the instances. So on that sequence diagram, every time you saw DA, that's what's finding the item and populating the instance for the actual class, for the actual object that gets created. So the customer object is more or less derived from that customer DA object. So the customer DA object goes and gets that stuff from the database to populate the specific instance. Cart item and online cart ask DA classes to save them. So they go out and tell the data access class to save the contents of the cart item or the online cart. So adding a view layer. So fill shopping cart use case, which we've been looking at. Not only do we have to add a data access layer, but we also probably need to add a view layer. So that's what this sequence diagram shows us. So we've added, notice that the stereotypes now say view. Now this is only a partial drawing. Before you saw that entire sequence diagram for this entire use case of filling a cart, but this sequence diagram sort of cuts off everything to the right of the cart handler. So we're only seeing the stuff from the left of the cart handler. We don't really need to see that other stuff in this diagram, but obviously in the in the real world you would add this stuff to the real sequence diagram. It's just hard to show all that stuff in a presentation, of course, or in the textbook. So here we've added the search item window, the add item window, the customer login window. All that stuff has been added as view classes. So, and that's why we have the view stereotype on those. But the cart handler is the domain class. It's a domain class because it's part of that core business logic that we've been talking about. So we would have added, by the way, I'll take a step back. We would have added to if we're using the view model controller or the 3-layer architecture or the 3-layer design pattern, we would add these view classes to our diagram, just like we added the data access classes to our diagram. So just to kind of review real quick, we started with the core domain model. So we started with the core domain or business process or business logic classes that we've been brainstorming all along, which were derived from the analysis. So in the analysis phase, we came up with the business logic and what the system needs to do. Then we converted that into classes for object-oriented design. And then because we're using the 3-layer architecture for our system, we expanded both sides of that by adding to the right side our data access classes and to the left side our view classes. And that's the basic steps we took to get to this design pattern. So designing with UML communication diagrams. So we've talked about sequence diagrams. Now we're going to just kind of real quick touch on communication diagrams. We did talk about communication diagrams previously in the analysis phase. So we'll talk about that a little bit in the design phase as well. So in the design phase, you have here, this is basically what a communication diagram would look like. You've got your objects, and you basically show all the messages that those objects have, between each other. It's a little bit redundant. It does show sort of the same thing that your sequence diagram shows, only this doesn't typically show you that over time, and it's only usually between a few objects. You would normally do this for particularly complex interactions between different classes. So here's another example. Again, this is taking your fill shopping cart use case and showing it as a communication diagram. So updating the design classes. Up until now, we haven't really changed the design class diagram very much, but our design class diagram focuses on the domain layer. When an object of a class receives a message, that message becomes a method in the class on the domain class diagram. So anytime it receives a message, that has to be a method in the. So if you show any messages on your sequence diagram or your communication diagram, those have to manifest themselves as methods in the class, which is what you see at the bottom here. So we have attributes in the middle. At the bottom, you've got your methods. Those methods, anything you show on the sequence diagram, which is one reason why it's helpful to do these sequence. Notice that throughout this whole process, we didn't sit down and draw a complete class diagram for the design and then draw a completed sequence diagram. We kind of did all this sort of together, right? We started with our first cut design class diagram, and then we created a sequence diagram from our system sequence diagram. And now we're going back again, and we're going to update that class diagram and add all the methods for any communication that we brainstormed on that sequence diagram. And really, when you do that sequence diagram, part of the exercise is showing you, all the different interactions that have to happen in order to complete that task or to complete that use case. If inventory item receives the message update quantity, then a method signature is added to the inventory item. So here we have update quantity added to the inventory item because we know that that's a message that the inventory item received. So now this is our updated class diagram, and notice now we've got all these all the methods or all the method signatures now on the design class diagram. And again, those all would have. Most of those we would have found in our system, on our design sequence diagram. So once we come up with our system, and let me take a little step back here, we've got all these different classes for our system. And again, this is only representing one use case. When we start to really build the system, it's typical to divide all this into packages, right? So if you take a look, this is a common way to do this. We've got our view layer, our domain layer, and our data access layer. This is one way that you could create these packages. So all of the classes that have something to do with the view layer would go into one class or into one package. The domain layer would be in another package, and the data access layer would be in a different package. Different programming languages manifest this in different ways. So in Java or .NET. So in Java, it's a package. In .NET, it's a namespace. In C++, it's something else. In C, you're in C# rather, it's something else, and so forth and so on. So this is just an example. What you're trying to think about here, though, when you do a package diagram, is how are you going to group these different classes in when it's created as physical code. So that's more or less what you're doing here. So issues with the three-layer design: the view layer, class responsibilities, display electronic forms and reports. It has to capture input events such as clicks, rollovers, and key entries. It's going to display data fields, accept input data, edit and validate input data, forward input data to domain layer classes, start and shut down the system. These are all the things that the view layer class is going to be responsible for. Your domain layer class responsibilities create problem domain classes or persistent classes. So that's all the stuff that we keep track of in our system. Process all business rules with the appropriate logic. And again, this is a lot of what we were doing in the analysis phase, is figuring out what those business rules are and understanding that logic. Prepare persistent classes for stores to the database. Your data access layer class responsibility. So once stuff is ready to either go into a database or we need to get stuff from a database, it's going to be the responsibility of your data access layer. So it's going to establish and maintain connections to the database. It's going to contain all SQL statements. So you wouldn't typically want to do SQL statements from your domain layer, but instead you would have a data access layer that does that. So the domain layer passes an object to the data access layer, which then goes and talks to the database. Process result sets the results of SQL executions into appropriate domain objects, and disconnect gracefully from the database, which is important for a variety of reasons. All right, so this is the summary of everything that we talked about in this unit, or at least this part of the unit. There were 2 presentations in this unit, and this was the second part. If you have any questions, please let me know, and thank you for watching.